Hey, this is Brock Lemire's, and in this video I'm going to talk about resistance and Ohm's Law. Okay, so resistivity is a property that all materials have, and resistivity is denoted with this Greek symbol rho, and it describes how much a material impedes or resists the flow of current. So as you can imagine, this is a very important concept within electronics and electricity because we want to push current through a lot of different materials and make the circuits do things for us, like give us light and give us heat. So when you look at things like a conductor, something that's a really good conductor, something that allows current to flow through it very easily or not impeding the flow of current, we would say that it has a very low resistivity. Insulators, which do not allow current to flow through them, we'd say that that has a high resistivity. And then, of course, semiconductors are somewhere in the middle. Okay. Now, resistivity is an interesting thing because it's not terribly useful by itself because it's an intrinsic property of a material. And so it exists within the material. It does have a units of what we call ohms meter. Okay, so this is the ohm symbol right here. And of course, that's named after some guy, George Ohm, who worked in this area. And we don't really use resistivity directly. What we do in electrical engineering is we use this thing called resistance. And so resistance is a value of an object. And so what we do is we say, okay, resistivity is an intrinsic property and it scales with like the volume of the object. Okay, so this is the equation for resistivity. It's basically the resistivity of the material, and you go look these values up in tables. So you can look up copper, you can go look up silver, you can go look up aluminum, and then you take that value and you multiply it by the length of the object that you're building, and then you divide it by the cross-sectional area. And then when you do that, you come up with this value resistance, and that's what we really use. We want to use this value of the thing that we have right there, and we want to use that in our equations. And so if you look at it, resistance is defined as the ratio of the voltage to the current. So we can technically say that the resistance is the ratio of the voltage across an object to the current that flows through it. So you right away you're like, wow, this is a big one, okay? So because we're going to be using this to calculate how much current goes through something based upon the voltage that I put through it, based upon a property called resistance of that object. Okay. Their units of resistance is ohms. Okay, so we immediately have what we have here. Now in electrical engineering, you can treat things as a resistor. Okay, you can say, okay, this object is a resistor. We actually have components that are called resistors, and then we also have a property. We also can apply this property to just other things. So you might have a wire that is, a mile long. You say, I'm going to treat that as a resistor. Okay, I'm going to say it has a single resistance, and so we use this in a lot of different things. So not only did old George Ohm get the unit named after him, he actually got the whole law named after him that describes the relationship between voltage, current, and resistance. And it is known as Ohm's Law. So Ohm's Law, this is the big one, okay? We use this so much, it is incredible. And one of the reasons we use it is because obviously voltage and current, those are the two quantities that we care about, okay? Those are the big ones. And then everything that we run current through has some form of resistance. And so we're constantly looking at this and saying like, well, if I do this, what what happens? If it has this much resistance and I put this much voltage, what are we getting here? One of the first things we look at when you look at this equation is what we call an IV curve. And so this is something that is very common in electrical engineering when you look at circuits, and it's basically a plot of the voltage versus current, and this is kind of really what we care about, right? So for these curves, what you do is you put on the independent axis, you put voltage, and then on the dependent axis you put current. And what you're trying to do is you're trying to show how does this current flow as you increase voltage across it, okay? And of course you can actually even go negative. But for a resistor, you're sitting there going, okay, so I've got V is equal to IR, except that this is actually kind of in a the opposite form, right? So it's like we want to actually have I be the independent variables. We kind of want it out of there. So let's do this. Let's divide both sides of the equation by R, and that it'll cancel. And so then we're left with I is equal to V over R. And so if we wrote that a little bit more standard form, what you'd get is I is equal to 1 over R times V. Okay, so you got your independent, and then you got your dependent out here, and this is essentially a straight line where this is the slope. Okay, so the slope is going to be that, and then you have the plus y-intercept, which is 0. It doesn't exist. And so if you look at this, it really looks like this. You have a line that goes through 0 and increases, and you look at that and you're like, well, no kidding, right? I mean, if V is equal to IR, and this is the equation. If I increase V, the current goes up. And it's, no kidding. It goes up linearly with 1 over R, which means that the slope of this line is actually 1 over R. Okay, so this is just something that you always see in electrical engineering. If you actually went negative with the voltage, it would also give you a negative current. And that's okay too, because if that was negative, this would be negative. It's not a big deal. Resistance is always positive, 0 or above. Okay, so now if that was just like a normal resistor IV curve, what would something like this, what do you think something like this would be? What if you had something like that? Well, what would happen is that you put a tiny bit of voltage and the current goes through the roof, right? And so this would be like a really good conductor. That's what the IV curve would look like. In fact, it would even probably be closer to like this, right? Really good conductor. And that means that the resistance is super low, right? So the slope of this is going to be very big, right? I mean, it's going to be almost approach 1, because this is getting smaller and smaller, not approach 1, approach big. So the resistance is getting lower and lower, so this number is getting bigger and bigger. So then a small change on the voltage results in a huge change on the current. So then to wrap that up, what would the last one be? So what if you had an IV curve that looked like this, where it was just like, I just put so much voltage on there and I get like no current at all? Well, that would be what you have as an insulator. Okay, so that would be what it looks like there, and that's where your R is like super big, and then your slope is really small. Okay, and so that's kind of one of the first things that you always look at with a resistor is let's talk about its IV curve. That's what you first do when you look at any sort of electrical component. Okay, so now here's how this works. We need to start looking at, we want to put a voltage across something. We want to calculate the current. But at this point, it's time to start learning how to draw circuits. Okay, so we're going to draw a circuit. And what we need to draw a circuit is going to be circuit symbols. Okay, so we need symbols. Okay, so let's start right off the bat with the symbol for a resistor. What you do with a resistor, okay, resistor, is it's a 2-terminal device, and you do a little squiggly, and you go like that. So that right there is a resistor, okay? And then you typically put an R next to it. Capital R means it's a resistor, obviously. And then you typically put its value. So let's just say we had a 150 ohm resistor. We now have our first symbol, okay? Now, we can't do much with this. We need some other symbols to actually form the loop and show what we're happening. But actually, if you remember, we have covered some other materials. For example, we've looked at kind of like sources, right? So of battery, we've seen pictures of batteries. Why don't we just take a symbol for a battery and call that a voltage source? Okay, so this is going to be a voltage source. Okay. And what we do here is we're going to draw it like this, a circle, and then since it's got a polarity, we go ahead and put a plus and a minus on there. So we know which terminal, okay, these are going to be the terminals or the nodes that it represents. So this is the positive side and this is the negative side. And then what we do is we put the voltage next to it. So we might say V is equal to 9 volts. Okay, 9 volts. All right. Now, you probably have heard in electricity this notion of AC and DC. Okay, so AC and DC, and we'll go into more specifics about what AC and DC are when we look at kind of electrical energy generation. But in general, AC stands for alternating current. Okay, and what that means is that versus time, okay, versus time, the current and the voltage, okay, so if you plotted it, it's going to move, okay, it's not going to stay consistent. We have looked at DC, okay, so this is direct current, okay, and what it does is if you look at the current on a direct, it just is flat. Okay, so if we had like, this is time, and that is, our current right there, and this was 9 volts, okay, so this is like 9 volt coming out of our 9 volt battery, you would have this, it's just flat with time, okay, so that's roughly the definition of AC and DC. Now, we always call it AC, DC, so it's current, but it also refers to the voltage, so anything that's moving. So when I come up here and I put this voltage source, I have a DC voltage source because I draw it like this. If I wanted an AC voltage source, okay, what I do is I draw a little squiggly line and a little sine wave. So I would do it like this, and I would still have a plus and a minus, but I would have a sine wave in there. And then that tells me that I'm doing AC, okay? So right now, what we have looked at, though, is we have an understanding of this. We had to put the DC voltage across a material in order to get the electrons to flow. And this is what we're talking about right here. And it turns out that these can be real items. And what do I mean by real? Well, it's like, okay, there's a voltage source. There's a DC voltage source, a 9 volt battery. So you got 9 volts there, you got a plus for the plus terminal, you got a minus for the minus terminal, and that is a DC voltage source. And I also have other ones too, right? It's like that was a 9 volt battery. This right here, all these round ones that you see, these standard, this is a AAA and a AA, these I'll give you 1.5 volts. Okay, this one gives you 1.5, this one gives you 1.5, and then of course you have the plus up here and then the minus down here. And so these are things that exist in the world, and so do resistors. So resistors are interesting because a resistor can be a thing. Okay, so this is an example of we call it a coaxial resistor. This is a resistor that we use a lot of times when we breadboard things or prototype it, and because you can take this wire and you can stick it into a breadboard, and the color codes on here give you the value of what the resistor is, but that is actually a little resistor. And there's also other forms of resistors. So if you look at this is a little printed circuit board, and you can kind of come in here and there's smaller resistors. So like, for example, when you come in here, these little fellas right there, I know they're kind of hard to see, but they're little tiny resistors. These are like, they're 60 thousandths of an inch by 30 thousandths of an inch, or 40 thousandths of an inch by 20 thousandths. So they're the same thing though. They have 2 terminals and they have a value of resistance, and we can calculate the current through them when we put a voltage across them, knowing their resistance. So these things are real components. Now, like I said before, though, you could conceivably apply the concept of resistance to some other thing. For example, let's say you had like a wire, okay? So you have this wire, and it's like if you measured from the red to the red, it potentially could have some resistance. And you could say, okay, I'm going to model this piece of copper or aluminum in here as a resistor, and that's fine too. So you kind of have this notion of, you have discrete resistors, and then you also have resistance as a model for the way current and voltage apply or flow and are induced across some structure. Okay. All right. So what does this mean when we come to draw circuits? Okay. So now let's take a look at how we could draw a circuit. So our first simple circuit is going to be something that looks like this. Let's just put a 9 volt battery across a resistor. Okay. So we'll put it like that. And here's what a circuit starts looking like. First and foremost, you're going to have our voltage source, okay, plus and minus, and there it is. And then what we're going to do is we're going to have a resistor. And what we will do is we will connect them up, and I'll have a resistance here of 150 ohms. And then over here, I'll have a voltage of 9 volts. Okay. All right. Now I'm going to introduce an important concept, which is going to be ground. Okay. This right here is called ground. In electricity, in electricity and electronics, we have this thing called ground, which represents a voltage of 0. Okay. And it turns out that we like to use that because when I say I have 9 volts right here, it's 9 volts between this terminal and this terminal. Okay. But nobody says what the lowest voltage is at. For example, if this was at 0, this would be at 9. But I could put this at like 15, and this would be at 24. So the 9 volt can actually kind of float around. And so what we like to do is we like to lock down the lowest voltage to 0 volts. And it turns out that if you just take a rod of metal and jam it into earth, it's ground. And that's because the earth is abundant in electrons. And so it's got so much, it's got so little resistance. So the electrons are so free to flow through the ground that it can never develop a voltage. Okay. And you're like, I don't even understand what you just said. Well, check it out. V is equal to IR. And so if you have a resistance, which is 0, if you say the earth is so abundant in electrons that its resistance is 0 ohms, no matter what, you can never get a voltage across it. So it's always at 0. And so that's what we do with like buildings and stuff. We jam a rod into the ground, and then that is essentially that's the earth ground for the building. Well, in circuits, we also have that concept. Okay, so we also want to have this notion of ground right here, which is going to be this theoretical 0 volt. When I do that now, the ground wasn't important for this circuit, but it's an important thing that we always draw in electrical circuits. Okay, so that's the concept of ground. Now, I want you to notice something. This is a loop. Okay, that is a loop. That means this is a circuit. Okay, remember a circuit. Electricity has to flow always in a loop. And now when I look at this, I notice my two things that are connected right here. This is obviously the source. Okay, so that's obviously the source. And why is it the source? It's because it is what provides the energy to run the circuit. And then this is going to be the load because it is just a passive device that does something. In this case, it just resists the flow of current, but it is doing something. That is an act, I guess. So this is the load. Now, when I look at this, just by inspection, I notice that I have this line right here drawn from here to here. That means that this point is the same as that point. When you draw a circuit, this is another important concept. These lines right here, okay, these lines are perfect conductors. So they're perfect conductors. And what that means is that when it's drawn as a line, it's not a resistor. Okay, it doesn't have any resistance. It also has, so it's no R, and it also has no delta T. It has no delay. So that is an ideal conductor. Okay, and if you said, well, wait a minute, I do have a wire that has resistance in it. Well, it's like, well, then put a resistor in there. Write a little squiggly for a resistor, okay? You got to model it. But if you do that, if you just draw a wire, that means that everything is perfect. Okay, so now we're sitting here, and it's like, all right, by inspection, just because this thing, the positive side is connected to here, I have positive there. They're the exact same point, and I also have the negative there. So my 9 volts here is also 9 volts there, and that's not magic. That's how I connected it. Okay, I connected 9 volts, right? I put 9 volts across this resistor. So I actually sat there and I just did this. I go, okay, boom, boom, 9 volts across that resistor. There's nothing magic about that. Now though, check this out. I can actually calculate the current that flows through this resistor. And I'm going to go ahead and draw an arrow, okay, and I'm going to label it I. This is pretty cool. Let's calculate what that resistor is. How are we going to do it? Ohm's Law. So V is equal to IR. And so let's plug in what we know. Well, I know that my voltage across the resistor is 9 volts. And I don't know my I. That's actually what I'm solving for. And I know my resistance is, for this example, 150 ohms. So now all I got to do is get the old calculator out and fire it up. So let's go ahead and go boom. Let's see here, get the calculator up. All right, so here we are, and I'm going to go ahead and say 9 divided by, I guess technically I should write this out. So 9 volts divided by 150 ohms, and so I get 9 divided by 150, and it comes out to be 0.06 amps. So I is equal to 0.06 amps, or said another way, okay, I is equal to 60 milliamps. Okay, and if you get used to converting between amps and milliamps when you see stuff like that, so if you didn't see that, you just apply the conversion factor. You'd go 0.6 amps, and you'd say, okay, I want to convert. Let's see, so it'd be 1 times 10 to the negative 3 amps is 1 milliamps, and off you're running. So then if I did that conversion, I'd have, let's see, 0.06 divided by 1 exponent 3 negative, and I'd get 60 milliamps. So I did that in my head, but you know how to do that conversion now. But holy cow, look at what we just did. We just calculated the current. This is awesome. So we just did it. We built a circuit, we drew a circuit, we understand the nodes, we understand the ground, okay? And then we understood that the way we connected it, I had a voltage across the resistor, and now I calculated the current. Okay, so now here's one last thing that I want to mention. What's the current through this fella? Well, current flows in a loop. So by inspection, if I just look at this, this current right here is also the current down this wire or this line, right? And it is also then the current right here. And then it also is the current here, and it flows like this. Don't worry about ground right there. Ground just sets the lowest potential, the lowest voltage. But this current is flowing in a loop. And it turns out that's exactly how it works. That is exactly how current flows. It cannot flow in an open circuit. It has to be in a closed loop. And in this very simple case, you've got that. Okay, life is good. We did it. We calculated. We used Ohm's Law to do this. Okay, very cool. But what's even cooler about Ohm's Law is that it works in all directions. Okay, so let's take a look at just doing a whole bunch of calculations of Ohm's Law. And so let's just take a look at, let's look at another symbol here. That's kind of a cool thing. So we had talked about a DC voltage source, okay? Well, you can also have a DC current source. So you could also have a source that provides a DC current. And the way that we denote that is we do it with an arrow. So this is going to be a DC current source, and let's say that it was 3 amps. Okay. Same thing with like the alternating current source. It would be something like this, where you'd have a squiggly, and then you'd still have the line in there. Yeah. Sometimes you could also draw it like you could put the arrow outside and have it be a squiggly. But these are DC. So these are current sources. Okay, ideal current sources. All right, so let's do some rapid Ohm's Law. Let's just say that I had, a circuit that was I is equal to 3 amps, and I connected that to a resistor that was equal to, let's do 150 ohms, same resistor as last time. Then I slap my ideal ground in there, and I say, what is the voltage across that resistor? Well, we kind of already looked at this, and it's like, well, okay, so if this current's going to flow here, it's going to flow in a loop. So I know that this current is flowing like this all the way around. So I know that the current through the resistor is 3 amps. So I can come over here and go, well, Ohm's Law, V is equal to IR. And what do I look for now? Well, I want to find the voltage. And so I plug in the current, which was 3 amps, and then I plug in the resistance, and it is, don't even need the calculator for that one, it is 450 volts. Okay, so I quickly solved that. Okay, life is good, life is good. Now, it works every which way, right? So it's like V is equal to IR. So if you wanted to solve for voltage, there it is. If you wanted to solve for current, you would divide both sides by resistance. You'd have V over R. And then if you said, well, I want to solve for resistance, well, you'd start with V equals IR, and you'd say, what would you do? Let's come over here. Divide by I on both sides, so you'd get R is equal to V over I. Okay, so kind of these equations right here allow you to go any which way. And that brings us to kind of one kind of final funny thing. In the beginning, people were like, well, I'm going to come up with people really didn't like doing algebra, so they came up with this Ohm's Law pyramid that I have here. And so you have this triangle here, and I'll show you how this works. It's V, I, R, and the way it's supposed to work is it reminds you of these 3 equations. So what you do is you say, if I want to solve for resistance, then V over I. It's V over I. So I can cover what I'm trying to solve for, resistance, and it's going to be V over I because the V is above the I. So V over I. And if I want to solve for I, notice that the V is over R. So it'd be I is equal to V over R. And then here, it's like I want to solve for V. So what I'd have is V is equal to IR on the same level, and it's Ohm's Law again. So apparently they said, this algebra is just too much for me. So I need like a graphic to remind me how to do this very basic algebra. But there it is. Anything and everything that you want to know about resistance, current, and voltage is governed by our buddy Ohm's Law. All right, that is it, and see ya.